So let's take a look at this first few problems here where we're being asked about the domain of these given functions. And what's going to be key for those is that the directions right here say you've got to watch out for things that could potentially be a zero in a denominator, you'd be dividing by zero, or taking a root of a quantity that would be negative. So the thing we're trained to do is look for denominators that have variable quantities, like we have in example 1, and square roots where the radicand might be negative, like we have in example 2. However, if we don't have any of those things, if we're not dividing in the problem and there's no square roots in the problem, we have a default kind of position that the domain is going to be all reals. So this last one is just a quadratic equation, and the domain for that is going to be all reals because we're not dividing by anything that could potentially be 0, and we're not taking any square roots. And of course what that means, what we're really asking is, what is x allowed to be? That is, what are all the values that x can be, and get a real number as a result when you plug those numbers in. So a parabola, of course, this x squared minus 3x plus 5, who knows what it looks like. It might look something like that, might look something like that, who knows, but it's certainly not going to be disappearing anywhere along the x-axis. So we get back to these first problems. Number 1, you see a denominator of 2x minus 3, and what we want to make sure happens is that 2x minus 3 is not equal to 0, because if it was, we'd be dividing by 0. So if we solve this little equation, we would get x cannot be 3/2. So if you think of a number line, 0's here, 3/2 would be over here somewhere. We'd want to make sure that x is not 3/2. So any number except 3/2. So anything down that way, anything up that way is okay. Negative infinity is over here, positive infinity is up here. So our domain is negative infinity right up to 3/2. We use a soft bracket or a parenthesis to indicate that we're not including 3/2. Then we pick up after 3/2 with a soft bracket or a parenthesis and proceed all the way up to positive infinity. Remembering that we always use parentheses on infinity because we can't include that value. So now for the second problem, we're looking at a radicand, the thing underneath the radical, that could potentially be negative. So we want to make sure in this problem that 5 minus 2x would be greater than or equal to 0. It's important to realize that having that quantity be 0 would be okay because you'd just be taking the square root of 0, which of course is 0. So if we can solve this inequality for x, we would add 2x to both sides and then divide by 2. Get 5/2 is greater than or equal to x, which is the same as x being less than or equal to 5/2. So think of a number line again, and 0 would be here, 5/2 over here somewhere, and now we can be 5/2, and we can be anything to the left of 5/2, anything that's less than that, all the way down to negative infinity. So the way we denote that in interval notation is parenthesis, negative infinity, up to 5/2, and because x can be 5/2, we use a bracket there. So there's your domain for those 3 questions. Could you see something more complicated on a test or a quiz? Sure, in that maybe you could have a square root in the denominator. So now if you had something like the square root of x minus 3 in a denominator, you'd have to make sure, because of the square root action going on, that this quantity is positive, 0, or I should say really non-negative, 0 or positive. However, because it's in the denominator of a fraction, you want to make sure that it's not 0. So that would add a little complexity, and we would have x minus 3 would have to be greater than 0, or x would have to be greater than 3. Because if x, normally if it's just a square root, it would be okay for x to be 3, because it would be the square root of 3 minus 3, which is the square root of 0, which is just 0. But because that's in a denominator of a fraction, having x equal 3 would be a problem. So there you go. Basically just look for denominators and what values of x would make denominator 0. and then look for square roots and look for the radicand to make sure that the radicand isn't negative. And that's really all you need to understand for domain for this part. Now, as we look to this number 4, we're being asked to graph the function that's given on a calculator. So we can draw a quick sketch on the coordinate plane that's given here, and then we should be able to find coordinates of maximums and minimums. Or if it just has a minimum, great. If it doesn't have a maximum, or if it just has a maximum, that's great. It doesn't have any minimums, whatever. We'll see once we get a picture of the graph. And then what the goal is to find out if we can describe when this function is increasing and when it's decreasing. So it wouldn't be a bad idea to think about the domain of this function, though. And you figure, okay, this is one of those things we just talked about where we are taking a square root. So we would need to make sure that our radicand, which is 2 minus x, would have to be greater than or equal to 0. And if you add x to both sides, that would be 2 is greater than or equal to x, which is like x is less than or equal to 2. Which tells us something. For sure, without looking at my calculator, but to graph this thing, I can promise you this graph is not going to exist over here to the right of x equals 2, because x's have to be to the left or equal to 2. And that's really what domain is telling us. It's like, where's the graph going to exist along the x-axis, and where's it not going to exist? So we know for sure that the graph must only exist over here. You know, it's going to exist from 2 out that way. So let's take a look at what it looks like on the TI and then copy it onto our paper. Okay, well, I graphed it on my calculator and gave it a quick sketch here. I didn't pay too much attention, other than the fact that it really looked like it crossed the x-axis right at the origin, right there, and it looks like it comes up and then comes down and plunks out, dives, bombs, and ends when x is 2. Now, both of those should make sense, that the x-intercepts are at 0 and 2, because if you think about plugging x into this function, when x is 0, it's going to be 0 times the square root of 2, which of course is going to be 0. So the y value is going to be 0 when x is 0. Likewise, when x is 2, plug a 2 in there, you're going to get 2 minus 2, which is 0. The square root of 0 is 0. And plugging a 2 in there will give you 0 times 2, which of course is 0. So those are your x-intercepts, 0 and 2. Now, it looks like the graph is increasing all the way along this part, up until there it maxes out somewhere right around, when x is 1, maybe a little bit to the right of that. And then it decreases down until x is 2, when the function just ends right there. So we need to find that maximum, and we can do that using the calculator, using the second calc max option. That's when you hit second trace, and options 3 and 4 are minimum and maximum. And if you choose option 4 for maximum, the calculator lets you pick a left bound and a right bound. And when you pick the left bound somewhere like 0 and the right bound 2, it's going to find the highest y value in between there. And in doing that, looks like that occurs when x is 1.3333, blah, blah, blah. So we can round that to saying that that maximum occurs, we'll use 3 decimal places, at 1.333. I'm going to use 3 decimal places, and we'll see what the y value is there. I'm just going to check on my calculator, and it looks like the y value there is about 1.089. 1.089. So what's important is that the function, I'm going to kind of highlight in green all these places where the function is increasing. So it's increasing up until that point. So that would be negative infinity to 1.333. And that's it. So that negative infinity that's coming there, that means that my x values over here, for all the x values to the left of what we see here, the y values are going to be increasing. This thing is going to be moving up as you move to the right until you get to 1.333, in which case it's going to start going down. So we can say the decreasing part of our curve, so let's highlight that in blue. The decreasing part is right there, which is from 1.333 to 2. Now, notice I mentioned it in class, but I'll say it again. For increasing, decreasing intervals, don't worry about soft brackets or hard brackets. Always just use soft brackets, and that way we can just use that as a standard convention. I'm never going to take off to try to catch you when I'm doing something wrong. Intervals for increasing and decreasing, I just use soft brackets for. So that's pretty straightforward, and hopefully that makes sense to you. So as we look at these next two examples, and we're talking about increasing and decreasing, we can continue to think about everything we do with our functions. For example, we always want to think about the domain. So for this one, number 5, you look at that denominator and you say, hey, x better not be equal to 3. So because if it is, we'd be dividing by 0. And we've talked several times, particularly recently, about if you have a value of x that makes the denominator 0, that does not also make the numerator 0. For example, 3 would make the denominator 0 here, but it wouldn't make the numerator 0. The numerator is busy being 1. When that happens, you're going to have a vertical asymptote. So I like to draw my vertical asymptotes in red to kind of reinforce the fact that you don't go near them, so as if they were burning hot or something. So this graph is going to have a vertical asymptote there. Now I can check this on my calculator, you can, but trust me, this graph is going to look something like this, where it's going to come down and go that way, and then on this side of the vertical asymptote, it's going to kind of go like that, and it's going to kind of continue out there. We can tell from our other study that the degree of the numerator is 0. There are no vectors of x in the numerator, and the degree of the denominator is 1. So we have a bigger degree of x in the denominator than we do in the numerator, which means our function is going to level off at 0 on both ends. So I've kind of shown that here. So if you think about this as far as increasing and decreasing stuff, that's our graph. That's everything about the graph right there. Increasing means as you move to the right, the y values go up. But if you can imagine this red dot here, as it's moving to the right, it's going down ever so slightly. Now it's going down a lot. Now it's just flying downwards. So that graph, the graph, rather I should say, is decreasing this entire time, because as we move to the right, it's dropping. So it's decreasing there from negative infinity, which is way over here, all the way to negative 3, being the x values. And then again, if you think about what's happening to the right of 3, it's going to start way, 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 way up there, but as you move to the right, it's coming down. So this function decreases to the left side of the intercept, and it decreases to the right side of the intercept, or not the intercept, the asymptote. Be careful. Don't let these arrows fool you. You might think, hey, this thing's going up. Well, look what direction my red dot's going. It's going to the left as it's going up. As you move it to the right, it's going down. And that's what it means to be decreasing. So as far as intervals of increasing on this thing, there are none. It's never increasing. This thing is decreasing from negative infinity to 3, and then it starts decreasing again once it gets to the other side of the vertical asymptote, and there you go. For this one, number 6, maybe a slightly less interesting function because it doesn't have any vertical asymptotes. There's nowhere where this thing is going to be undefined, because this is a function where we do not have any division. We're not dividing by anything that could be 0. We're not taking any square roots of any potential things that could be negative. So this is going to be a less interesting function in the way of having parts where the function is going to break up or have discontinuities. But it does have some interesting stuff as far as increasing and decreasing goes. To do that, I would consider this function by factoring it and realizing that we could take an x out, and it would be x squared minus 9. And of course, x squared minus 9 further factors to x plus 3 and x minus 3. So it's real easy to see where this thing would be equal to 0. I use the triple line equal sign there to show that I'm setting this thing equal to 0, because I'd like to know where the x-intercepts are. Well, 0 would make this thing 0 if x were 0, so it's going to have an x-intercept at the origin. Negative 3 would make this factor 0, so it's going to have an x-intercept at negative 3, and positive 3 would make it 0. So if I come along and drop those x-intercepts in there at negative 3, 0, and 3, I'm going to be good to go. Now, you can check this on your calculator, but this graph is going to kind of have this sort of look to it. It's going to come up from down here, it's going to turn around, come back down, and then head back up there. So I'm going to check it on my calculator so I can draw it somewhat accurately on the graph here. Okay, so I've got this thing graphed, and I was able to use the second calc max and min feature to find out that maximum occurs at negative 1.732 as an x value, and the y value is 10.392. And similarly, over here at positive 1.732 and a negative, oops, I forgot my little negative sign on my 10.392 down there. There you go, negative 10.392. So what we've got is a function that is increasing in a couple of places. I'll use green for increasing. So this is all going up as we move to the right, going up as we move to the right. And then that happens again over here. We're going up as we move to the right. So those are the two intervals where we're increasing. So that happens, you know, all of these x values are making that stuff happen, and all of these x values are making that happen. So we are increasing from negative infinity, which is way out here to the left, positive infinity is over there on the right. So from negative infinity to negative 1.732. That means our graph is going to be coming up during those times. And again, from positive 1.732 out to positive infinity, those y values are going to be moving up as we move to the right. So I'll just put that in interval notation there. And we can say negative infinity to negative 1.732, and then union that with 1.732 to positive infinity. And decreasing, I'll use red to highlight that. That's the stuff in here, which is happening in between those x values of negative 1.732 and positive 1.732. So for all these x values in here, the function is moving down as you move to the right. And so we can identify that. I'll label it in red, and here we go. Negative 1.732 to 1.732. And there you go.